Yeah, I hope everybody's having a great summer and cross fingers this haze on top of us will disappear over the next couple days. Let me share my screen quick here. If I can make this all go. Um, Bear with me just a second. There. You guys seeing that okay? Great. Um, Well, thanks so much. Just a few remarks about me before I launch into this. I've been at Syracuse University since 1998. My training is in marine geology and marine geophysics, but I've spent much of my career studying large lakes. A lot of the work that I've been doing, my group has been doing, is on the large lakes in East Africa. So we've been very fortunate to have been able to work over there on a regular basis, but it's always delightful to come home to upstate New York, to central New York, and work on and visit and play in fantastic lakes like Skaneateles and Owasco Lake right around here. So let me just advance. I just learned that this is a 20-minute presentation, not a 40-minute one. So I'm going to cut parts one and two way back, probably. Just to say a few things about the geological background of our region, how geologists study large lakes or even medium-sized lakes. And I'm mostly going to focus on sections 3 and 4 here. Let me just bring my pointer up if I can find it. Uh, no, it's not going to work. Well, I'll just stick with the cursor. In any event, I'm going to focus mostly on parts 3 and 4. One of our doctoral students just finished a project on Skaneateles Lake, looking at nutrients spatially around the lake margin and also over the last couple hundred years. So that's been a very interesting outcome. And we're currently carrying out a multi-beam echo sounder study on Skaneateles Lake. This is a new instrument that we acquired a couple of years ago. It lets us acquire very high precision bathymetry, also backscatter information, which gives us information about the nature of the lake bed as well as water column data. And this is in support of some harmful algal bloom research we're trying to carry out. And let's see if I can advance. There, I just wanted to acknowledge a few folks here. And I understand John is in the audience. I haven't caught up with you in a while, John, but I want to acknowledge Hank Mullins, late Hank Mullins, who was professor at Syracuse for about 30 years. He introduced me to the Finger Lakes, and I've had opportunity to work with John on and off around my career. He and I were grad students together way back when. I've learned tons from John and from Hank over the years. So it's I just want to make note of these guys. Hank really laid the groundwork for a lot of us who have been studying the geological aspects of the Finger Lakes in his time at Syracuse. Currently, I'm collaborating with Charlie Driscoll and Melissa Chipman of Syracuse. We've got a terrific technical staff in our research team. Right now, Doug Wood is leading the charge on our multi-beam echo sounder acquisition on Skaneateles. He's an old salty dog, had worked at NOAA for 12 years and is helping us out tremendously in this project. I've had a couple fantastic doctoral students engaged in the work. Mackenzie Brannon just defended her dissertation 2 weeks ago, and I'm going to present some of her work here. And Nick Brennan is an incoming doctoral student who's going to pick up where Mackenzie left off. And we've also had a number of excellent undergrad students working with us contributing. Jack Arnstein is out with our team now. And I want to just mention we've had some very supportive foundation help over the years. The U.S. National Science Foundation has helped us acquire our new multi-beam echo sounder instrument, as well as supported our technical staff. Skaneateles Lake Association has been fantastic over the years, directly supporting some of the work, the spatial nutrient study, for instance, and allowing us to use their research boat regularly and really promoting our studies. We've had support from Water Resources Research Institute for our down core historical study, and Sam and Carol Nappy have been super generous in supporting our current multi-beam echo sounder study, and Syracuse University itself has provided direct support as well over the years. It's been great. So I'm going to skip over some of these these initial remarks. I'm not going to say much about modern ice sheets, but just to say that we can actually learn a lot about modern ice sheet processes by studying the deposits of ancient ice sheets, like are all around us, right? So our landscape has been greatly modified, of course, by the very thick ice that sat on top of us in the Pleistocene. This is a map of Antarctica, of course, and it's just illustrating the different colors represent the velocity or the speed of ice movement, which has really only been recognized clearly over the past 20 years. But these bright colors are zones of ice streams where ice can move very fast and serve to basically drain the volume of the ice off the continents. And our area had ice streams right on top of it in a number of places, especially around Oneida Lake, but other places as well. Just a quick reminder, uh, much of our much of our region, our entire region, was covered by 1.5 miles of ice about 24,000 years ago, part of the Laurentide ice sheet, this last most famous glaciation of the Pleistocene, one of many. But that ice began receding perhaps 21,000 years ago, give or take. And by about 12,000 years ago, that ice was 10 to 12 to 10,000 years ago, that ice was on the northern edge of Lake Ontario or even farther north. So that's it's had a big impact on our region, of course. And I don't have to spend any time talking about the dimensions of our lakes. You know those well. I did want to mention, do a quick compare and contrast between the Finger Lakes and Oneida Lake, which we've been studying as well recently. Oneida Lake occupies what was an extension of Lake Ontario, basically, and it occupies this very broad, flat plain that was the site of a major ice stream at about 12,000 years ago. In contrast, the Finger Lakes um, are incised into this high Appalachian plateau, which was, and those valleys were deepened and steepened upon a pre-existing drainage network as a consequence of multiple ice advances. So I'm going to skip over this glacial geological or this superficial geological map. Um, just to mention that we have a lot of really interesting deposits around here, and studies of these deposits outside of the lakes and under the lakes can tell us a lot about ice sheet processes, and that's been a rich path of research for many of us. Just a quick reminder, as that ice sheet pulled away from its maximum advance, which was all the way down to Long Island and northern New Jersey and northern Pennsylvania, as it pulled back, it thinned a bit along its edges, and it opened up drainages that went out to the Atlantic Ocean. But in front of that retreating ice margin, there were very large lakes were positioned there. So there was actually an enormous wall of ice present at the northern ends of the Finger Lakes for quite a while. And these lakes were probably much deeper, much colder, much less productive than the Finger Lakes that we know today. And this was a very dynamic place, right? Massive waterfalls and so forth at the on the margins of the system. Um, our whole region was dominated by the predecessor to Lake Ontario. We call that Glacial Lake Iroquois. It covered all of what's now the Oneida Lake Valley up into the Mohawk Valley. The St. Lawrence Valley was largely covered, and it extended way up into Cayuga Lake. Cayuga has the lowest elevation of all the Finger Lakes, and that region was flooded during the time of Glacial Lake Iroquois. But we don't think Owasco and Skaneateles were directly connected necessarily, but there was a lot of similar kind of sedimentation and similar water bodies in there. So backing up a little bit, I'll just ask the question, what is a lake to a geologist? We actually study ancient lake deposits as well, and we think about this a lot. To a geologist, a lake is a hole in the ground that's filled with water. So the first question always is, how was that hole made? And in the case of the Finger Lakes, we know it's associated with erosion attached to the big ice sheet. But there's been a lot of conversation over the years about exactly what process was at work. The conventional wisdom is that sort of traction and erosion and carving by the ice itself right on the bedrock was responsible for deepening these valleys. Other folks, including the late Hank Mullins, would argue that it was also the release of high pressure water at the base of the ice sheet, basically a big hosing back and forth across the valley that contributed to that that erosion. So those are among the principal ideas for the formation of the Finger Lakes. So geologists, marine geologists, limnogeologists like to study lakes using a couple key tools. We use geophysics, especially acoustic surveys, including seismic refraction and reflection, but also coring and drilling. So up on the upper right is a photograph of one of these instruments that we routinely use. This is a towfish or a transducer array that sends sound signals down, which bounce off the bottom and then return to the towfish where they're collected. And these sound signals produce these reflections, and we fire off these transducers about 3 times a second in a lake such as Owasco. And those seismic signals propagate down through the water column, through the sediment column. Some of that energy bounces back up, and those seismic signals are generated by changes in the sediment density and the sound speed. So different types of sediment yield very different responses. We collect lots of these traces or these data series, and we pull them all together in a profile form, and we can get a picture of a slice, a vertical slice of the subsurface. So that's essential to a lot of the kinds of things my group does. This is an example of one of these. We combine the geophysics with core sampling. This actually isn't from either Skaneateles or Owasco. This comes from Oneida Lake. But we take these core samples in various ways. Sometimes just a pipe going over the side of the boat. Sometimes we use rotary drilling, in fact, to recover these. But we collect these tubes of mud in plastic tubes. We bring them back to the laboratory, we slice them longitudinally, and we curate them very carefully. We take images of them in various ways. This happens to be an X-radiograph. Then we'll take subsamples for all kinds of basically forensic analysis. Okay, we'll do all kinds of studies using geochemical methods, using geophysical methods, using geological methods to analyze layer by layer going down the sample there. So this is an image of one of these profiles across Owasco Lake. This is data that John Halfman and Hank Mullins worked up way back in 2001, and we've captured the digital data and sort of brightened it a little bit from the original work, but we can very nicely see different packages in here. So this is about 5 meters. This transparent package we see at the top. Can you guys see my cursor okay? Carol? Yeah, okay. So this is roughly 5 meters thick up at the top, and then we have a thicker layer that's more reflective down through here. And these represent very different types of sediment. In the uppermost part, we have some relatively organic rich, more homogeneous material, dark brown. The layers down deeper, though, are pinkish in color, many of them, and highly layered. These are, in fact, this is a series of proglacial lake varves. These are seasonal deposits that accumulated when there was still ice in the catchment, in fact. And one important thing to note is that the accumulation rate of these sediments was vastly higher, faster accumulation for these highly reflective guys than for the stuff over the last 5,000 or 10,000 years of sediment here. Just another snapshot of some of the data that Hank and John worked up. This is a major slide deposit from the margins of Owasco Lake. Sometime a few thousand years ago, there was basically a catastrophic event that introduced, probably quite rapidly, based upon the character of this feature, rapidly introduced a large volume of mud into the basin. We don't know what instigated this. You know, was it a climate event? It could even have been some seismicity, some earthquake shaking might have cut this stuff loose and sent it into the basin. We see it here in Owasco. We see similar kinds of deposits over in Skaneateles, and we think they're about the same age. So whatever its causative mechanism, it was not just localized to Owasco. It was sort of a more regional signal. When these slides entered the lake, it would have been catastrophic for the lake margins, right? There was probably a local tsunami that was generated that washed up all along the shoreline. So it would have been devastating for anything living along the margins in all likelihood. Now, the landscape has moderated and stabilized greatly since that time, we think. But given the steep sides of these basins, this is not something you could ever rule out completely occurring again in the Finger Lakes, right? We have some very steep margins in places, and a significant slide would induce a local tsunami if it were to occur. Right, so this is a summary figure from one of Hank's earlier papers describing the general evolution of the Finger Lake valleys. We had ice occupying and deepening these valleys for a while. As that ice retreated, it shed off icebergs. Some of those icebergs themselves dropped off coarse pebbles, sediments into the lake, very distinctive deposits. It continued to retreat, and then once it left completely, the landscape altered, vegetation really took hold, sedimentation rates slowed dramatically over that interval, starting around 8,000 years ago. So one interesting feature that we observe in our geophysical data at the northern ends of almost all of the Finger Lakes are these so-called zones of erosion or wash zones. So this is a profile from Skaneateles Lake. It cuts across east-west or west to east, just about 1 mile south of the village of Skaneateles. And you can see that we've got some of this more recent sediment, a thin layer of this 10,000-year-old sediment package. Then the highly reflective stuff is here once again in Skaneateles, but then it all disappears in what we call this wash zone. This is actually going to be pretty important. I'm going to come back to this in just a little bit toward the end of the presentation. So just comparing the modern watersheds, I'm sort of advancing now to present some of Mackenzie Brandon's work. If we compare the modern watersheds of Skaneateles and Owasco, there's huge differences, right? Skaneateles watershed has a lake surface area, or watershed area to lake surface area of 4.3. It's actually the smallest of all of the Finger Lakes. In contrast, the Owasco watershed to lake surface area is 17. It's the largest of the Finger Lakes. And this actually produces pretty significant differences in water clarity and quality, and probably plays a role in the frequency of occurrence of harmful algal blooms as well, quite possibly. Mackenzie Brandon, who defended her dissertation just a couple of weeks ago, did a couple of projects of interest. She used, so I'm getting to the third part of the presentation now. This project used surface sediments to try to characterize the differences in quantity of nutrients and sediment character around margins of the lake. And she also used some sediment cores that go back a few hundred years to characterize different lake conditions and try to understand how those nutrients cycled in these systems. We've known for a long time that the most important of these nutrients is phosphorus. It's the limiting nutrient for cyanobacteria that produces these harmful algal blooms. And the phosphorus is intermittently stored and released from sediments. This is well known, well documented. But we wanted to try to characterize whereabouts we have abundant phosphorus and where we have less abundant phosphorus in the sediments, and also assess how quickly that material might be released on a regular basis. So the key questions were, how do sediment and pore water phosphorus distributions differ around the lake? How do those distributions relate to water depth, geochemistry of the sediment itself, organic matter and organic content, texture of the sediment, and so forth? What can this tell us about phosphorus cycling in this kind of oligotrophic lake? Oligotrophic lake is just a very clear water system, which is unproductive in terms of biological activity. So for this project, we acquired 130 grab samples from around the lake margin. And of course, the lake is an important water supply, And the increasing frequency of these algal blooms has become a greater concern, of course, especially since 2017. Um, so uh, these grab samples were taken in relatively shallow water, um, somewhere between 40 and 250 meters offshore, up to a maximum water depth of about 30 meters. And we captured the upper few centimeters of sediment in each of these samples. A whole array of different types of geochemical analyses and sediment analyses were carried out. I'm just going to show you the results of a couple of these here. Excuse me. Um, Probably the most important one for our discussion today is the one on the upper left, where we can see a trend of increasing phosphorus in the sediment with increasing water depth. It's a very consistent trend, and we have a sort of 2 to 5 times increase in phosphorus over this depth range. We see some other interesting relationships as well with phosphorus and other elements, but I'll leave those for the discussion afterwards. On the right, we have the same plot as the upper left, but this is showing the same data broken out by individual transect, right? So we have these 130 samples that are taking in individual transects extending out from the shoreline. So there was an interesting study that we contributed to and published by Mike Kelly from RPI last year, published in Limnology and Oceanography. The RPI team had a buoy positioned at the northern end of Skaneateles, recovered a lot of interesting data and in the water column, and made a lot of measurements. We contributed the sediment data for this. And they developed a 3-part model, which suggests that there's a sequence of events which may be responsible for driving some of the very largest of the HAB events. And this occurs when in August or September, generally, when we have a well-developed thermocline, a very strong boundary between the upper mixed layers and the deeper layers in the lake. As the wind blows over a few days, we get a surface seiche rocking back and forth, but some of that energy propagates down to the boundary between the upper waters and the deeper waters, and that starts to rock back and forth. And when that wave hits this northern zone where we have shallow shoaling, that's where we see some erosion, or what they've called the wash zone. And following these events, that sediment that is greatly enriched in phosphorus compared to the shallow sediments is brought into the uppermost part of the water column. It's entrained up there. And if there's a stilling event, that is, the wind dies, that's optimal conditions for enabling very large harmful algal blooms to occur. Right? So it's this 3-part sequence: strong winds rocking the thermocline, eroding and disturbing the phosphor-rich sediments, and training it into the upper water column, and then a stilling event. And they documented quite nicely that this occurred a number of times in Skaneateles. So I'm sure there are many reasons, or many mechanisms, I should say, for stimulating, producing harmful algal blooms, but this seems to be a viable one for the large ones, and is perhaps somewhat unique to the Finger Lakes, because we've seen this same erosion zone, the same wash zone is present in Owasco Lake, in Cayuga Lake, and in Seneca Lake. So it's a commonplace, it may be a commonplace condition here. So we want to investigate this wash zone a little bit further. What's the extent of it? How enriched are those sediments? If we go deeper than 30 meters, how enriched in phosphorus are they? How deep is that erosive zone? So that's really the focus of one of our current projects, which I'll get to in just a second. So just to summarize the main observations from the surface sediment project, we observed that phosphorus bonds really readily to the finer clay material, the fine-grained stuff, so it's stored farther offshore and it's enriched. Inshore, the phosphorus is quite depleted, comparatively depleted. There's a fair bit of calcium carbonate forming in the shallow water, so this may in part be a dilution effect.
Not to try to strain my head like this.
Sorry? Um, So just very quickly, I wanted to show you the results of some sediment core work that we carried out that Mackenzie led as part of her doctoral work. The question was, how have the key nutrients not varied spatially, but how have they varied, fluctuated through time? Um, we know there have been some very dramatic changes in the watershed, land use changes, climate change likely influenced the storage, and so we wanted to investigate those changes over time. So we took 4 sediment cores. We used, again, the Lake Association research boat, the Bob Werner research boat, fantastic tool. We used this precision coring system to collect these undisturbed samples and carried out a whole variety of analytical work, layer by layer by layer, down those sediment cores. So these are the locations of the different cores. A very important aspect of the work is to get precise age dates on each of those layers. So we took these tubes of mud, we extruded them at half-centimeter thickness intervals, and then we analyzed them first for their age, geologic age, using a method called lead 210, and also a method called by measuring the amount of cesium-137, which is a consequence of both nuclear testing and the Chernobyl disaster. We can detect when that occurred. And from that, we can set up a timeline, and we determine that our northern core has a basal age of about year 1800, and our southern core has a basal age of about 1815. And so very quickly, just show you a couple of results. We see that very consistent increase in phosphorus concentration and also accumulation, as well as increases in calcium and, for the most part, increases in mass accumulation rate as well, in both north and south. We do see a decline in mass accumulation rate in the north as a consequence of reduced mass accumulation rate, which is interesting. So maybe a consequence of some land use changes in the northernmost part of the Skaneateles catchment. So just to summarize these main observations, we see those rates accumulating steadily following European settlement, colonial period, when there was widespread deforestation, there was expansion of agriculture, urbanization, and really in the latter part, starting in the middle 20th century, there was really an intensification of agriculture as well, which we think is contributing in addition to any potential climate changes. Right. So I know I'm over time here. I'm just going to very quickly show you what we're doing in Skaneateles Lake right now. So this is using multi-beam bathymetric echo sounder, multi-beam echo sounder for bathymetric and backscatter analysis. So this is an instrument that it's an acoustic technique as well. It's a little different than the seismic profiling method I described earlier, but this sends out sound energy to the sides of the boat and broad swaths. So our instrument actually sends out more than 1,000 beams to the side of the boat, so we can collect a broad swath of information as we sail the boat over the back and forth across the lake. So these are some data that we acquired back in a year ago in 2024 in the lead up to this project. And I just want to build out on that a little bit. Now, some folks have asked us, well, why bother mapping the detailed bathymetry of the lake bed? Seems like a lot of work, but I would argue that it's pretty important. We spend a lot of time and energy analyzing the watershed, right? We have all these GIS layers, the planners pour over our maps of the watersheds themselves, but there's actually very little information about the spatial distribution of material in the lakes themselves, which are the sinks or the sumps for the watershed discharge. So we've made the argument that it's valuable for infrastructure. I'm going to show you a picture of the Syracuse city water pipe that needs work here. It's valuable for accurate water budget analysis or analyzing hydrodynamics in the systems. It can be used for calibrating satellite and drone imagery if you're trying to map turbidity in the lakes. Obviously, it can be an aid for navigation. There's information about shipwrecks. We can get quite nice information about bottom type, sediment grain size and texture, vegetation extent of bedrock, and so forth. And it also gives us information about bottom habitat for native or introduced or invasive species in these systems. Our group's primary interest, though, is to map the extent of these sediment, these nutrient-rich reservoirs in the sediment, the phosphorus-rich mud on the lake bed. So that's a major outcome that we're pursuing. Um, I'm going to skip over this guy a little bit. There was some older data for Skaneateles. There is some single beam older data for Owasco, which is useful, but this new data will provide complete coverage in between the survey lines, right? Um, and we're generating now in Skaneateles these digital terrain models of grids of 0.5 to 2 meter cell size grids. So very, very useful. And along at the same time, we're collecting this backscatter data, giving us information on bottom type. So here's just a snippet showing the city of Syracuse water intake. This is the spatial distribution of pore waters in this system. Again, we want to study this wash zone where we see an increase in phosphorus in the deeper waters. This is an example of some of the backscatter data that we're collecting. So on the left is a zoom in of this area from the northern part of Skaneateles Lake. We can discriminate sand from gravel or hard ground from the fine-grained muds through here. So this takes a bit more processing to do well, but we can characterize or we can make maps of the bedrock type, the extent of vegetation, and so forth quite readily from this system. All right. So I'm about done here. Just wanted to show you what we're up to. Our team has been out since late June and making great progress. This is an example of the bathymetric data we've collected so far as of this past Monday. There's a lot of texture. There's a lot going on here. We sort of expected to find a very flat lake bed, but there's pockmarks in different places. There's some interesting channels. And that wash zone up in the northern end is really quite complex. So there might be an interesting story to derive from this. You can see quite a number of erosive features here at depth. So we're going to combine these new bathymetric data with our seismic profiles to better understand the development of this zone and determine the area, the extent really of that wash zone where there's this phosphorus-rich mud. Right. So in conclusion, I'll just say that our multi-beam bathymetry data has been pretty interesting. We're finding shipwrecks. We're finding out a lot of information about the lake bed. The backscatter and sediment analysis can provide detailed information about the source of these phosphorus-rich sediments, potentially a significant player in these large harmful algal bloom events. The other thing to just remind everybody about is that these sediments of the Finger Lakes, these deposits have a fantastic archive of information about past environmental conditions. It's not just the lake. We can actually learn information about the atmosphere and the region by studying these samples in detail. So I look forward to chatting further. I'm happy to answer questions, and we look forward to working with you down the road. Thank you.
Okay. Are there any questions for Dr. Scholz? Go ahead and raise your hand. Oh, I see one raise. Constance, go ahead. I think you might.
Okay, can you
There
hear
you
me
go.
now?
Yes.
Yeah, I live in Ithaca and I'm a scuba diver and I dive in Skaneateles Lake quite
Oh,
often,
great.
which is one reason this talk attracted me. It was really interesting. My question is, there's an area in Skaneateles Lake, I believe it's kind of down south, and it's supposed to be fossils in a wall of corals and things from
Right.
when it was underwater.
Sure,
And
sure.
apparently you can see them. I haven't been to that dive site yet. I have to get there. But do you know anything about that? And when it
So
was formed and
there's
yeah,
outcrops on shore where you can go to, and you can see the Devonian Rugose coral fossils
Devonian,
quite
yeah,
readily.
yeah. Oh,
I've
okay.
done a little bit of diving there myself, not too much. I've never seen any rock faces in the water. I would love to find those.
Oh, okay.
But
Okay.
you can go onto the rocky beach there and I think it's part of the Finger Lakes Land Trust Preserve, one
I
of them.
think it is now.
And
Yeah.
you can find beautiful corals, rugose corals, Devonian corals, just lying spread out
Devonian
around there.
roof.
Yep.
Okay.
Yep.
Fabulous.
Yep.
So there's nothing in the lake proper underneath it.
Yeah, I don't have direct knowledge of that.
Yeah,
There
I
could
have
be, and there may be some expert divers out there that have found a rock wall where you can see them, but I have not been there myself. I'd love to find it.
Yeah. Okay. Thank you. Great
bet.
talk.
I also have a question from Bill Foster about financing the map of the Owasco Lake. Where, Bill? Are you able to ask your question?
Yes, Carol, actually what I'm asking, like, what would it cost to finance similar research on Owasco Lake that you're currently doing on Skaneateles Lake?
Well, it might be easier to talk offline. I haven't looked lately at, the rough bathymetry of Owasco. It's interesting. This instrument that we're using on Skaneateles is relatively new to us, and we were out there for 2 weeks and basically got no data until we got the thing dialed in, and now we're really making great strides. When we collect these data, the swath that you collect is 3 times the width of the swath is 3 times the water depth. So it's sort of counterintuitive. The deeper water you go, the faster the more data you can collect more quickly. Okay, so in lakes where there's a lot of very shallow water, it takes you a lot longer to get complete coverage. Bill, I'd be happy to work up that number for you. We have a team now of 3 people. We have a boat donated to us. One of those 3 people is a funded graduate student who's going to do the bulk of the work. Another person is a highly trained technician. So, we have to pay those folks salaries. So it's on the order of $100,000, perhaps. Now I'll tell you this: if you were to hire a contractor to do that, it would be 5 to 10 times that. If you were to hire a commercial contractor like the government does for NOAA, it would be 5 to 10 times as much. So that order of magnitude. It might be less, might be a little more.
Okay, I have one question since I don't see, I do see some others, but I'll just ask this real quick. I want to make sure, one of your findings early on, you said, is you see an increase in phosphorus in the sediment with an increase in water depth, correct? I have that right?
Yeah,
Okay.
that's right.
Okay, that was great, thank you.
A lot of the sediment, the shallowest water is pretty low, shows pretty low values of phosphorus. And there's a couple of reasons for that. We could perhaps talk offline about that.
Okay, great, thank you. Now I see there's Ellie Berry has a question.
Thanks.
And
First,
then
Krish,
there's
thanks
Jim
so much for doing this and for speaking with us. That was great. The question I have is, do you suspect that these wash zones that are mixing into the Epilemian during these siege events, do you think that the sediment is more likely to be hundreds of years old and more so legacy phosphorus, or do you think it's newer from the past couple of decades and recent runoff events, or potentially a mix of both, or research is to be determined?
Yeah, that's a fantastic question, and that's one of the key ones for us. We don't know. Clearly, there's been erosion occurring there a long time. In the fairly shallow subsurface, there's actually proglacial lake deposits. And we haven't really analyzed these in any rigorous way for their phosphorus abundance. And that's at the top of the list, is really to look at this more critically. Yeah, you zeroed in on one of the key things. Thanks.
Yeah, of course. I'll be looking forward to seeing it all come out. I'll be keeping a close eye on it all and reading some of the ones you referenced. So thank you.
You bet.
And then I see Dana has his hand, and then after that it'll be Bill Hecht and Jim Long.
So Chris, this is Dana.
Yeah, hey, Dana.
Terrific presentation. I wish we could slow you down and go through it a lot more thoroughly. So we
Sorry.
may ask you to do that sometime. But I wanted to ask, what causes the separation of I'll call them aggregates. I don't know if that's the right word, but sand from mud or sand from gravel.
Right.
What causes that
Right.
to occur?
So, and that's a great question. I mean, the natural process in the lake is for the wave action in the shallow waters is going to winnow out the fine grained material and gradually move it toward the center of the lake, right? And there's not enough wave energy really to move the sand and gravel from the margins where it's washing in. There's not enough wave energy to really, most of the time, to push it into the deep part of the lake. So the bottoms of the lakes are almost always covered with relatively fine grained material. It's this, this there's a natural sediment focusing process that concentrates the clay sized particles, the really tiny ones, into the deep part for the most clay and what we call silt sized particles. They're generally finer than 60 microns in size. So yeah, that's the short answer. There are other ways of getting coarser grain material into the deep basin via density flows, hyperpycnal flows, but those are usually more localized in lakes like the Finger Lakes.
Thank you, Chris.
Sure.
Carol, if you're talking, you're muted.
Well, that would explain it. Next, we have Bill Hecht. He had a question about the height of the lake. Bill, are you?
Can you hear me?
Yes.
Hi, Bill.
Hi. Since the Skaneateles has been raised 11 feet, is that showing up in any of your information? And the water intakes from the city of Syracuse, does their withdrawals induce any kind of current that would show up?
Ooh. Well, the first question about the height of the lake, I think I've heard some folks say it's even more than 11 feet from the natural position, but it's that order of magnitude for sure. One impact of that raising, that damming in the village, is that it's greatly increased the size of the littoral zone, the littoral zone, right? The shallow waters. The whole north end of the lake was just swampland, right? Prior to dam construction in the early 19th century. So all of a sudden we've created a lot more lake area that's very, very shallow water, that's prone to growth of macrophytes, that's facilitates the accumulation of calcium carbonate. And so this has been a discussion amongst our group is, just the raising of the lake level itself. Have we introduced new terrain for the carbonate factory, right? Is there more area for carbonate accumulation? And is that sort of altering the sediment geochemistry, at least in the shallow waters? Is it diluting the phosphorus to a certain extent and so forth, right? So, that we haven't seen a direct influence of the dam. Our cores only go back to 1800, so that's right around the first of the dam construction. Probably to really analyze it rigorously, we need to go back a couple hundred more years. And maybe that's something we'll do down the road. We certainly see this significant increase in calcium carbonate accumulating in the lake, and that's not unique necessarily to Skaneateles. We see that in Oneida Lake. I've heard it described, and John Halfman might be able to jump in and remark on that as well. As far as I know, that's observed in other places in the Northeast. I'm sorry, your second question was about the
City of Syracuse,
currents. Yeah.
which raises another question. When Hank was doing his work back, I guess in the 80s, I know at the north end of Cayuga Lake, he couldn't get data because of the gas, methane in the sediments. I don't know if your instruments today can penetrate that.
Yeah.
And years ago, the city of Syracuse actually did an exploratory well at the north end. I'm not exactly sure, but I remember when Hank was doing his work and identifying certain gravelly layers under the lake. I was wondering as crazy as it may sound, instead of building a $250 million filtration plant, would it make sense to actually use the natural gravel filtration you've got in the lake sediments?
Yeah, yeah, interesting idea. I mean, you've probably heard that the city of Syracuse is really on edge because they have no more, um, uh, one more pink slip, and they have to build that filtration facility, right? They have one more penalty, and that's it. They have to spend that money, and it's going to be devastating financially, I think, for them to do that. Um, that's out of my wheelhouse. Could we filter enough water for the city? There's a lot of water going down that pipe. That's a big volume. It's an interesting idea.
It's like 52 million a day
Yeah,
that
yeah,
they
yeah, yeah,
permit.
yeah. 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 That's out of my wheelhouse, Bill. I can't help you
No,
with that one. Interesting idea, though.
with directional drilling, they could
Oh yeah,
drill,
yeah,
drill right down through that bed and then perforate the pipe
yeah. Right,
for a mile or two.
right.
Be easy drilling.
Yeah, that'd be interesting. Yeah, yeah. Cool.
Okay, we have Jim Long was asking, can sediment cores see evidence of acid rain? Jim, did you have another part of that question, or
Um,
I think that's
the short answer is absolutely. We have not done any of that analysis ourselves. Really, that the classical way of looking for changes in acid rain in sediments is looking at the phytoplankton, looking at the diatoms, the single-celled silica-rich algae that are commonplace in these lakes, and they're very sensitive. The different species are very sensitive to inputs of acid rain. So that is the classical way of doing it. It's something we've talked about in our group, but we've not done that yet. But it would be a logical thing to attempt in this area.
okay. We also have Frank Moses just said, thank you, Chris, for all your service and support of our Finger Lakes. And then Dr. Joya, and then after that we have Michael Pizzola and Michelle Henry. And then that'll probably be, well, we'll see how far we get. Okay, Dr. Joya.
Like in your graph, it looked like the phosphorus levels were going up as you get further out away from the shore.
Yeah.
Is the center of the lake, is it then become low, or do you have samples for the center?
We don't really have enough. We have a few samples from deeper water, but not enough. And if the stars align themselves, we're going to finish our multi-beam bathymetric survey this month, and sometime before the season closes out, we would like to do some samples in water depths of 30 to 60 meters, progressing farther south to really look at that distribution a little bit better. Yeah, we don't have enough samples right now, and it shouldn't take us too long to collect those. But that's crossing fingers that everything holds together. We want to get the acoustic work done first. Yeah.
Thanks.
You bet.
Okay, thanks. And then Michael Pizzola had asked what kind of shipwrecks are in the lake, and do you have any information on this topic?
We've seen a few bumps down there. We haven't analyzed anything too critically yet. Check in with us next spring. We should have a lot more detailed, follow the processing the full processing of the bathymetry will take us to the end of the year. To really see the shipwrecks well, we need to optimize our grid size and amp up the resolution. We have seen a couple things down there that are clearly interesting, and we know for a fact in shallow water down by Lord's Camp, there's a sizable boat that you can scuba dive to quite easily. So that's been around for a while.
Okay, and then Michelle Henry, how are you collecting near shore data below 3 feet?
Ooh, that as I mentioned, the shallow water data collection is really slow going, right? Because if it's simple geometry. Our swath is 3 times the water depth. So we're in 80 meters, we get these 250 meter wide swaths, and we get all kinds of data really fast. But when we're in 1 meter of water, it's a much smaller swath. It's also becomes a hazard net. You know, we don't want to chew up Frank Moses's nice propeller on his beautiful research boat. So we actually don't go into water depths really any shallower than about 2.5 meters. That's our limit.
Okay, and then I see Dana's hand is up again. Dana Hall.
Probably an easy one, Chris, but when I've been out with Bill Dean, we come across lots of tires. And is that your finding as well?
We haven't drilled down to that resolution yet. I think we'll see tires no problem in our data set, but there's a number of suspicious targets that are very likely tires, but we haven't finished the processing enough to really pinpoint them all. Yeah.
Okay, thanks, Chris.
Thank you. All right, is there any other questions? Folks can raise their hand or write a little note in the comments. Okay. I don't see any others. Speak up. Well, looks like we're gonna end exactly on time. Tremendous timing on your part. I did want to say thank you so much,
Sure.
and it was really interesting. And thanks to everybody who came and attended this and participated tonight. And again, don't forget our in-person board meeting on August 20th at 6:30 at Springside Inn. Is there anything else anybody wants to say? Dana again.
Carol, this recording will be available on, and when? On where and when?
I plan on exporting it tomorrow and getting it up on our YouTube. So I will also post on the website once it's on YouTube, and I can even push on social media just in case everybody needs a little spot to go to find it. But it'll definitely be on our website.
Thank you, Toy.
Right. And then, one other thing I was going to say is I got a lot of calls today about habs in the lake. Apparently they're with us and good and strong. There was one even sighted in one of the tributaries flowing into the lake. So reminder to everyone that you don't want to be in that. You don't want your dogs, your children, or anybody in that. And you can always report that to the state reporting page. New York State reporting page. So yeah, just wanted to remind you of that we know they're out there. It's terrible. The pictures I saw looked like pretty strong ones. So they're out there.
Carol, which tributary was it found in today?
Suckerbrook, right next to Julie's house.
Oh.
Yeah, she called me and said, if you want to run over right now, come over and see it. But I was at an appointment, so I couldn't do it. Yeah. Phil?
Yeah, just saw some foam in the lake a couple of weeks ago.
Already?
North end by the kayaking area, right off Emerson Park. I was just at the drinking water treatment plant today, and they said they haven't seen any cyanobacter in their filter paper samples that they do to screen for cyanobacter. So it's not showing up as pigment in their white filters, so it's good for them, but it's definitely it's in a lake in other spots.
Yeah, and really just seems to be earlier and earlier in August that we really see strong ones. Anyways, we know they're there and we're working hard. Anything else from anybody? Don't see hands. I see thank yous. It was fascinating. Thank you so much for the information, and good job, Chris.
Okay, thanks so much. Nice meeting everybody tonight.
All right, thank you very
Thank you,
much.
Thank you very much.
Have a good evening. Thanks. Bye-bye.
Thank you, Chris.
Take care, Allie.
And thank you, Allie, for coordinating.